the puzzle of the logic involved in solving the problems. So really what we want to do is think of this more as, kind of a word problem in math and less about the actual programming implications. That's why in this lecture we're going to use some logical diagrams. So briefly we can think of a selection statement as a piece of syntax that changes the flow of our program based on logical expressions. Up to this point we've been asking the user to enter values. Now we're going to be able to start to use selection statements to make some decisions about those values. For example, if I ask the user to enter their age and they enter a negative number, well, that's a really bad thing because people should be positive numbers in terms of their age. So we could actually make a statement that says, hey, you entered an incorrect value, you entered a negative age, we're now going to terminate the program. We haven't gotten to loops yet, so we don't really know how to go back and ask them to re-enter those values, but we could at least make a decision to terminate the program. So with selection statements we have some control. We could also do things like, if somebody enters the wrong PIN number, we could also terminate the program, or if they enter the correct PIN number, we could actually remove money from their bank account. If we wanted to write an ATM machine, we now have the capability to determine if the user has enough money in their bank account, then we would allow the withdrawal. If they don't have enough money in their bank account, then we would deny the withdrawal. So we can change how our program is operating based on logic. Now, decisions. Simply put, computers can only compare two things at any given time. They can either say, is this true or is this false? So if you have a complex decision that you want to make in the computer, what you need to do is break that complex decision down into the much simpler decisions that it's composed of. Complex decisions, even though you may not think this in your brain, are composed actually of many simple binary decisions. In other words, decisions that are yes or no decisions about a bunch of things. Something as simple as, should I take an umbrella today? You might think that's a fairly simple decision, but it's a complex set of factors involved. You're probably asking yourself, is it raining outside? Yes or no? No, it's not raining. Is it sunny outside? Yes or no? Well, it is sunny. Did the weather person say it might rain today? Yes or no? Do I really feel like carrying an umbrella around today? Yes or no? So something as simple as taking an umbrella with you on any given day is actually a series of very tiny decisions strung together that end up in your ability to decide if this is a path that you would like to take or not take. And that's why we need to think of all decisions in a computer system. Is this true or that true? Okay. Is this true or that true? Okay. Is this true or that true? And eventually through all of these little decisions between two things, we'll be able to get to the end of the branch where we actually want something to occur. So the takeaway is always break all of your complex decisions down into simpler decisions, which can often be a challenge, and that's really the challenge of this chapter. If we're using flowcharting, we have this diagram here in front of us that we can think of. The diamond in a flowchart means, hey, a decision is being made here. So you'll notice in the blue diamond in this slide, is this statement true? Your program's running, it hits a decision point. And at that point, the computer's going to ask, is this statement true? Is the user over 18? Yes, the user is over 18. Then we can allow them to sign up for a car loan. So it would go to the right and go to the yes branch. So is the user over 18? Nope, they're 16. Well, we can't sell a 16-year-old a car because they can't sign contracts, and if they wreck it, we'd have to eat the loss. This is what that statement looks like in pseudocode. This is not actual Java, but it's close enough to help us decide how to go about writing the real program. So notice we have if this is true, and this is true. That statement is actually between parentheses. In Java programs, as you've seen in the book and in other resources, that's where we put the expression. That's where the question is. And if that is true, we do the top part of the equation where it says do this. If what's between the parentheses is false, we do what's on the else branch. So we can compare these directly. We can say that if the statement in the blue diamond is true, we go to the yes side. In this slide, if the statement is true, we do what's on top. In this slide, if the statement is not true and we go to the left and we go down the no branch, then we would go to the else part of this statement. Okay, now what do we replace do this with? Well, actual executable Java code. And what do we replace this is true with? A valid expression. Do you always need the else statement? Like what if, something's not true, you don't do anything? Well, in this case, we don't always need the no branch. You don't always need the else branch in a decision. So your program runs, it gets to the statement, it says, hey, is this statement true? If it is, go ahead and execute some code. What if the statement is false? Don't do anything. If you are not the millionth customer at the grocery store, they don't do anything. If you are the millionth customer, balloons fall from the ceiling and noisemakers go off and you get lots of money. So you don't need a false branch unless you actually need it in terms of logic. A couple other things, if we want to make complex decisions, our program can have multiple if statements, and they can be nested inside each other. So we come down, we make a decision. It says, hey, is this statement true? If the statement is true, in this case, it's going to go ahead and it's going to end up at another decision. So we can actually have multiple decisions nested together. I could have easily put that decision under the no branch, but in this case we have multiple decisions, and we can actually have one decision then lead to another decision, lead to another decision. So this idea of breaking a problem down into multiple decisions and then putting them together in a way that, by the time we get to the end of that chain of decisions, produces the output we want, is definitely possible. Here's what that looks like in code. Notice the yellow code, in this case, represents the innermost decision on this slide. So in other words, the second blue diamond that's inside of the yes branch is represented by the yellow code in this slide. So you can actually see where the nested if statement exists and where the outer if statement exists. And what you'll realize is that the only way we'll get to that yellow code is if the first question or the first expression in the first set of white parentheses is true. Otherwise, if it's false, it just gets all skipped and we get to the else statement. So make sure you're comfortable with seeing how this flowchart represents or is represented by this code. What are the comparison operators in Java? One of the reasons why I've been trying to keep you from saying the word equals when using a single equal sign is because that is the assignment operator, And in this case, when we're trying to compare two things, the equality operator is actually two equal signs. So if we're trying to say is 7 equal to 9, which you would never say because it isn't, but you would use equals equals. So two equal signs is the way of asking Java, are two things equal to each other? And then greater than and less than, you've seen before. If you want to determine if two things are not equal to each other, it's an exclamation point and equal sign. And then there's also less than or equal to and greater than or equal to. And a point in the big blue arrow on the right-hand side. One thing you should know is that these operators are only for comparing primitive data. In other words, comparing things like ints, doubles, and characters. If you need to compare strings or you need to compare objects, then you need to get to the next slide. So let's talk about comparing objects. The only way you can compare two objects is if those objects provide a behavior. And again, the formal word for that is method. The only way you can compare two objects is if those objects provide a method to compare themselves to other objects. So you'd have to look at the API, you'd have to look in the book, and see if each object provides a way to compare itself. And you'll notice that in the string class, it actually provides the equals method, and you'll see that in my sample code. So if an object doesn't provide that functionality, there are ways that you can actually write it, and we'll talk about that later on in the semester, or you just have to deal with the fact that you can't compare two objects. In other words, what are we doing when we're comparing two objects? We're comparing the properties of those objects. If you use primitive operators to compare objects, what you're really comparing are the memory addresses that they point to. Remember that object variables don't contain the object, they just contain a memory address where you can find the object. Sometimes we actually want to do that. We want to see if two variables are pointing to the same object, but more likely than not in this class, at this point in time, you do not want to go about using primitive operators to compare objects. You always want to use their built-in comparative method. Java also provides if, else constructs. These are very nice when you're trying to put together chains of related logic. And so what's really nice about these features, if you're trying to compare a large number of, or make a large number of decisions based off a single value, the first expression that's true will terminate the entire if-else structure. And you'll see that in the book, that it's a nice way to short-circuit a bunch of decisions. I mean, if I'm trying to find a student in the class, and I happen to find, I say, hey, are you Jason? And you're the first student I ask, and you say, yes, I'm Jason. Then why would I continue to ask the 19 other people in class if they're Jason? It makes sense that when you find the first person, you stop asking. And in the case of if-else structures, as soon as you find a true expression, all of the other expressions are skipped so that the computer can save some processing time. The idea here is why keep comparing things if you found a true answer? And that if that's the functionality that you want, then this is the construct for you. Switch statements are just a convenience for creating if-else statements that are only switching on a single value. A lot of times in computer programs you'll see like enter P to print, S to save, D to delete, A to select all. So in that case you're asking the user to enter a single character, and based upon that single character you're going to execute a series of behaviors. So what you want to do here as the switch statement is, if you don't really understand why you're using them, you can actually just choose not to use them. But if you take a look at the programming code that accompanies the lecture, you'll notice that I do have some examples. I showed two parallel sets of code, one being an if-else statement and a switch statement that achieve the same ends. Another thing to mention is the Boolean operators are discussed in the chapter. Building complex expressions using the and or operators is not actually required. They really just provide you with a convenience for chaining together a series of decisions inside of the parentheses in an if statement, in other words, inside of the expression. So for example, we had this program logic flowchart earlier on in the lecture. So you'll notice that I've got two decisions, and earlier on we represented this by two nested if statements, but I can use something like the logical and operator to go ahead and kind of make this a little bit more syntactically compact. So in this case, you'll see that the second and this is true. The yellow component here is again representing the inner decision in this statement, but you'll notice that it's a little bit more simplified. There's actually some issues with this code, but I've oversimplified it. Actually, if you can find the errors, you could always just post that to the discussion board. But there's a couple things I'm